So in the same way that we can determine the concentration of an acid or a base by carrying out an acid-base titration, which we called volumetric analysis the other day, because we're doing the analysis based on volumes of solutions that we're mixing together, we can also determine the concentration of a solution of an oxidant or a reductant by doing a titration. There's only really two sort of differences between an acid-base titration and a redox titration. One will be that the numbers tend to be a bit more interesting. In an acid-base titration, it's always 1 to 1 to 1 to 1 mole ratios. But for redox titrations, the numbers can be much more interesting, and so there's a little bit more work in working through the calculations. But from a technical point of view, the main difference is that typically for a redox titration, you don't need to add an indicator. Right? You have an indicator in an acid-base titration because you're mixing colourless solutions and making colourless things. So you need an indicator to tell when you've reached the equivalence point. In a redox titration, you're typically using coloured things. So like permanganate, for example. And so you can pick the equivalence point by the disappearance or the appearance of some coloured molecule. So you don't need to add an indicator to tell you sort of about the equivalence point. The reaction will tell you it all by itself. Okay, so here's the sort of thing that we could give you. You have 20 mils of a solution containing iron 2 plus aqueous of unknown concentration, was titrated with a standard solution. Remember, standard solution is one that we accurately know the concentration of. So a standard solution of acidified permanganate ions of concentration 0.143 moles per litre. After 12.9 mils of the permanganate solution had been added, that should say, the purple colour persisted, indicating that no further reaction occurred. And so from that, determine the concentration of the iron 2 plus solution that you started with. Okay, so what we're doing then is we're adding permanganate to our iron 2 plus. The reaction is going to be as we're using the equation we've just developed. So when you add the permanganate out of the burette into the little flask which contains your iron 2 plus, as soon as that permanganate goes in, it will react with the iron 2 plus, and the permanganate will be turned into manganese 2 plus. And so that purple colour of the permanganate immediately disappears. Yeah? When the reaction happens. At some point, we will have added enough permanganate so that all the iron 2 plus has reacted. Right? So that's the equivalence point. When we've added enough permanganate to use up all of the iron 2 plus that was initially present in your little flask. If we add more permanganate than that, then that extra amount of permanganate has nothing to react with anymore. And so it stays in the solution as permanganate, and so it stays purple. And so the equivalence point here will be when the solution first starts staying purple. Because at that point, you're adding permanganate and there's nothing left for it to react with. Does that make sense? Yeah? And so that's your indicator. That's taking the place of the indicator here. That tells you when you've reached the equivalence point and all of the iron 2 plus is gone. So here's the reaction. We've written this down 5 times already, so we'll flick past that. You can get that from above, draw an arrow or something. So this is what I've just said. While there is iron 2 plus present, the added purple permanganate will react with it to form the colourless manganese 2 plus ion. The point at when the purple colour persists corresponds to the point when the last of the iron 2 plus has reacted. And so that's your equivalence point. And so the steps that we go through to do the calculation are going to be just the same as the ones that we used for our acid-base titration. Right? We have a solution of iron 2 plus that we don't know the concentration of, but we accurately know the volume of. And we have a solution of permanganate ions that we accurately know the concentration of. And by doing the titration, we now have a volume of permanganate that we had to add to reach the equivalence point. So the first step is going to be to calculate the amount of permanganate that we added, and we can do that by just using our little formula, amount equals concentration times volume, where the concentration is the 0.143 moles per litre that we were told in the question, the concentration of that standard solution, and the volume is the volume of permanganate that you had to add to reach the equivalence point. Okay, so the amount comes out as being 1.84 times 10 to the negative 3 moles. That's the amount of permanganate that you've had to add to use up all of the iron 2 plus that was in your solution. Okay, now if this was an acid-base titration, then you would go, oh, well, that was going to be the amount of the stuff that it reacted with, because it's always a 1-to-1 mole ratio with acid-base reactions. But with this one, it's harder. Yeah? If we want to work out the amount of iron 2 plus that amount of permanganate reacted with, we need to go back to our balanced chemical equation and look at the ratios of the stoichiometric coefficients for the permanganate and the iron 2 plus. What the equation tells us is that each time a permanganate ion reacts, it reacts with 5 iron 2 plus ions. Right? It's a 1-to-5 ratio in the balancing. So that means whatever the amount of permanganate is it reacts, it must react with 5 times that much iron 2 plus. And so if the amount of permanganate that reacts is 1.84 times 10 to the negative 3 moles, then that must react with 5 times that much iron before it reaches the equivalence point. And so the amount of iron that must have been present is 9.2 times 10 to the negative 2 moles. Right? That must be the amount of iron that was in your little flask. Yes. Yes, it should be, shouldn't it? Lovely, thank you. We'll change that. It's bound to be 3 on the next slide, but I hope. There we are. 9.2 times 10 to the negative 3 moles. And so then once we've got that, remember we want to work out the concentration of that iron 2 plus solution. And so step 3, calculate the concentration. The concentration is just the amount divided by the volume. We now know the amount. Oh, it's still wrong. Look at that. Sorry. There will be some more editing going on here. That should be a 3. And then we need to put a 0 in there.
No, the answer is 3.
Oh, really?
Yeah.
Oh, good grief. And so it'll be that. Okay, so the process is just the same. The only real difference, like I say, is in doing the calculation that you can't just assume that it's a 1-to-1 mole ratio. You have to do a little bit more thinking to relate the amount of stuff that comes out of the burette to the amount of stuff that's in the flask that it's reacted with. And then if you're actually doing one, the only difference is that you don't have to add an indicator. Right? You just can rely on the colour changes that you see for the reactants turning into products. Now sometimes you have to do some fiddling around to enhance those colour changes. So some of you may have done titrations where you use iodine and then you add starch to highlight the colour change from iodine going into iodide. That's a very common thing to do, but it's kind of like adding an indicator, but it's a bit different as well. In general, you certainly wouldn't add indicators like phenolphthalein or bromothymol blue to a redox reaction.